Hello, welcome to this Cyber 2020 keynote lecture. My name is Eckhard Flügel. I'm at the School of Computer Science and Mathematics at Kingston University in London, United Kingdom, and the title of the lecture is Game Theory for Security, Past, Present and Future. So what I will do is I will explain how game theory can be used in order to analyze security scenarios. So by presenting two fictitious case studies, I will show how the theory can be used in order to better prepare the defender against attacks. So before we start properly, let me just point out that the slides are actually available by clicking on the link below in the comment section of this video. So these are the full slides in PDF format. And for this talk, I will skip the technical ones because I want to focus on having the overview and the motivation rather than spending a lot of time on the technical details. So let me present the first case study. So I'm looking here at YouTube, in fact at YouTube channels and attackers who might compromise those channels. They might upload unsolicited videos or they might post misleading or illegal comments. And we want to obviously prevent this from happening. Now there are so many channels out there. There are actually more than 31 million YouTube channels available at the moment. And what we want to do is we want to save ourselves some work because at the moment there are staff employed who have to manually look at various accounts and see whether everything is all right rather than relying on the owners reporting it. And is there a way how we could optimize effectively this random screening, perhaps based on being a little bit more clever and looking at the attacker's motivation at the same time, trying to effectively find an optimal approach. And the second case study is quite different scenario. Let's say in an organization, in a company, we have software assets which might be out of date. So effectively, someone who is in charge of the software patching needs to identify vulnerabilities. And so what they found is that there are two vulnerabilities which need patching, but actually they can only patch one vulnerability at a time due to constraints with the resources and availability. And also the problem is that they compute the CVS scores, they can download the CVSS information for those vulnerabilities, and it turns out that they're quite similar. So really they're struggling with their decision, which software should they patch first, and hence is there a different way of perhaps computing a different score, still based on some of the CVSS subscores, but doing it in such a way that you could perhaps find a different picture and a clearer prioritization based on looking at the attacker's motivation at the same time. So before we can actually use the game theory for the two case studies, we need to be clear about the usefulness of the approach. And there are three conditions really which need to be satisfied. First of all, the games that we're looking at, they need to be sophisticated enough. They need to be powerful enough to actually capture the requirements of the scenario. Then second, the model will certainly require some additional assumptions, and these assumptions need to be valid in our specific case. And thirdly, and that's really important, that the game theoretical model is accepted by all the different players in the real world. So basically, both the attacker and the defender, they have to agree that game theory should be used in order to, model their payoff functions and their expectations. Otherwise, it would not be valid, and it's a problem. I mean, it's not clear whether that is really the case in the real world, but that's the fundamental problem of game theory anyway. And a lot of papers have been written on this aspect, which we're not going to look at in detail, but we're simply assuming that these conditions are met. So before I will talk about the first case study, let's just briefly review some concepts in game theory, and let's also look at security games. So in the game theory, what we're trying to do is we're trying to develop a mathematical approach to analyze a situation where different decision makers or the different players are engaging in this game, and they're motivated by basically actions or strategies, as we say, that they can take, and they will be rewarded depending on what move they have made. So the reward is basically specified in what we call the payoffs or the utility functions. And then obviously the different players, it could be 2 players, it could be any number of players, they would like to somehow optimize the outcome. And this will all depend on the specific type of game. There are lots of different approaches, but what we are interested here is the Nash equilibrium approach, which is effectively some kind of suboptimal solution where we can't always assume that that's the best for everyone. But if all but one players remain the same and only one player deviates from their specific actions, then they would be less well off, so they have no incentive to do that. So that's the idea of the Nash equilibrium. So what do we mean by a security game? In the security game, we tend to have 2 players, and they are actually an attacker and a defender in some kind of cybersecurity scenario. So they are driven by their aims to maximize their payoff functions, so they're rational players, and they are non-cooperative. Now, in our context, we are specifically interested in 2-player bimatrix complete information games. Bimatrix means that we can encode the payoff functions independently. So the attacker and the defender both have different rewards, and that's often called a non-zero sum game as well in the literature. So here, looking at bimatrix games and complete information means that there is availability for the respective players about the knowledge of the mutual reward functions, which seems somewhat artificial, but it turns out that quite often this is still a useful assumption. So let's turn our attention now to the first case study, and let's try to analyze the pertinent aspects of it, and let's see how that translates into the game model and the specific requirements that we would have. More information can be found in the slides. So it's clearly a 2-player game. We have the defender and the attacker. So you can see here, D is the defender, A is the attacker. So what would be the strategies? Basically, there is a large number of channels to be chosen. These are the targets. So the attacker can decide to, let's say, attack target T1 here or T2. And depending on which target the attacker attacks, they would get certain rewards. So here, if they target T1, they would get a reward of 0 if the target is covered by the defender, so whether it's actually protected. So the defender can choose between cover or uncovering of a target. This is clearly a non-zero sum game, as these payoffs and these payoffs are independent. And a crucial feature of this game model is the requirement of a large number of targets. They need to be fit into the model. We need to find an algorithm that is performed enough to solve the game. So this is done by what we call the massive 2-player security games, which have been devised in the literature for application scenarios such as this one here. And there's one additional property which is a typical feature in a security game. This is to do with the difference in payoffs, let's say here for the defender in this row. So if the target is, the attack target is covered, the defender typically has a higher payoff than if it wasn't covered, because then they would lose out on the attack. And for the attacker, it's the other way around. So they will be better off if the the target is actually uncovered. Now, the interesting thing about the massive security games is the appropriate data structure that we actually use in order to represent the game. Because this data structure here is quite a compressed way of encoding the game, and it's much more suitable than the standard normal form that we use based on 2 matrices, A and B, where in total, if you count the entries in those matrices, we have 32 here, whereas here we only have 16 in terms of the payoff values. So the standard notation here would be less efficient. So then let me just explain what the Matrix notation actually means, so here the matrix A is the payoff matrix for the defender, and B is the payoff matrix for the attacker. So let's focus on the defender. For example, if we look at the first column, this would mean that the target T1 is attacked. And if we look at the first row, this would mean that the target T1 is actually defended. So then you will find the payoff value 7 in here, again, which is here. And what we observe now is that in those cases here where the target T1 is attacked, so first column, but we're actually protecting, let's say, the second target or the third or the fourth, but not the first one, then we're losing out. So we have the payoff of 3, but that these are the same values because they are not depending on the actual, they only depend on the attacked target. Yeah, so I hope that was clear, but basically what it means is in each of those columns, there are always only 2 different values. So we have 3 times the 3, we have the 1s in here, again 3 and 0, and that's sort of redundant. And if we switch from this notation to the previous one, then we're saving some space, which makes it more efficient. So now let's proceed to the analysis and the solving of this game. So first of all, we're going to apply the Nash equilibrium concept here. It turns out that quite often for games of this type, we have a unique solution, x star, y star here, which is a very useful property. And x star basically gives us a probability vector, which shows us the likelihoods by which we should protect the different targets. And y star will be the expected attacks on the different targets. So for example, here we would observe that the target T1 doesn't seem to be very interesting for the attacker because here you find the 0 and hence we will also not really bother protecting it. At the same time, the target T3 seems to be of greater interest for the defender and the attacker. And then if both players would embark on this Nash equilibrium strategy, then they would expect it to have the following payoffs. So this is the value for the defender and this is for the attacker. So here the interesting property of the non-zero sum game is that actually one of the players can still be less well off than the others. So there's no clear winner or loser here actually. And the only thing really we can say is due to the properties of the Nash equilibrium, the player 1, the defender, knows that if they switch strategy while the attacker wouldn't, then they would be less well off, so they would earn less. And same for the attacker, if they deviate from their strategy whilst the defender is sticking with it, then they would also lose out. So hence, if they both adhere to the idea of the Nash equilibrium approach, they would come up with this as being their optimal solution. In the slides, we refer to this as a coverage vector, and then we can also develop certain feasible schedules from this, which would be more useful in the practical scenario that can be found in the slides. So then just to summarize the importance of the game theory here for the case study, thanks to the concept of the Nash equilibrium, we will have recommendations for the defender, how frequently to focus on the protection of the various assets. In other words, how to look at the various channels and scrutinize for the presence of malware or of any other illegal content. And at the same time, this model is quite efficient and it will be able to deal with a large number of targets, which is exactly one of the features in this scenario. Now let's look at the second case study. And if we are trying to find the game model that's underlying this idea of the software patching problem, then you will see that actually there are only 2 strategies now to consider for each of the 2 players. So we still have a defender, that is the software company or the company who are trying to either defend or not defend. So defend means patch the vulnerability, and not defend means to leave it unpatched. and then the attacker is obviously trying to either exploit the vulnerability or not. So here in this matrix normal form, we have effectively a bimatrix game, which is now written differently in terms of the first matrix corresponding to the first entries in each cell, and the second matrix, the attacker matrix, is the second element. And we are denoting the strategies SD and S minus D for patch, not patch, and similarly for attack, not attack. This is very much like one of these games that are typically explained to people when they learn about game theory, and you will find lots of information on the internet, for example, on the prisoner's dilemma. And here we have a similar sort of strategic game. And now the interesting feature of this particular game is the following. Let's try to understand the precise payoffs here. Let's start with the simple scenario where here the defender is not actually defending and the attacker is not attacking. So no one is actually doing anything. So there are no costs and there are no benefits. Hence we get 0 and 0. Now let's maybe move to a situation where there's still no attack. So we're still in this column, but the defender decides to defend. So they have a certain defense cost, minus C. And that's obviously on the whole a negative number. So really, they would have no incentive to do this. If the defender knows that the attacker is not attacking, they rather not defend, because then they can actually save themselves the cost of defending. So they would switch to this lower row here. So now let's try to reason what the attacker would do if they knew that the defender is not actually defending. Then clearly the attacker would prefer to actually attack the target. So then they would have a cost, a certain attack cost, and they would have a benefit from the attack. Given that the attack is not defended, it would make sense to assume that the benefit is greater than the cost. So overall, this would be a positive number. So then basically we switch, the attacker switches to attacking. Now, if we then again reason in terms of the defender, if the defender knows that they're attacked, they would switch to defense. So they would go up. So here it would make sense to assume that the loss that is occurring from the attack would be on the whole less than the actual defense cost. So we would go up here. And then lastly, if the attacker observes that the target is defended, then they would retreat, because then they can save themselves the attack costs. So this is a typical reasoning, what we do in the game theory, and really what it means is that there is no so-called pure Nash equilibrium. A pure Nash equilibrium would be a situation in which both participants, both players are happy with, because it would be stable with respect to changes of the other player strategy. But here there is no such thing, there's no pure Nash equilibrium. And then the theory, which has been developed by John Nash, shows us though that there has to be one Nash equilibrium. If it's not pure, it would be a mixed one. So basically the useful insight here is in a situation where it's not obvious really how we should proceed, because we have this dilemma, the game theory would tell us some expected probabilistic behavior that would give us some probabilities by which we should follow a defense or not defense strategy. So this is then summarized in the next slide. So the theorem 1 just says exactly what we have just found. By inspecting the game, there is no pure Nash equilibrium strategy. And then you can now, if you follow Nash's theorem and how he proves it, you can come out with the following result in the theorem 2, where we have a precise value P and Q for the probabilities, the expected value of defense and attack, which we would have in this situation. And now I will explain the main point of this game model and its link to the CVSS. So our problem here is we need to obviously find values. We need to find the different parameters here. How would we know them, in the real world? And so here the observation is that we can actually use the Common Vulnerability Scoring System, which is an open standard, which is available quite easily for a given vulnerability to look up some values which would determine the quantities, the loss of the defender and the cost for the attacker. So it turns out that they are given by the exploitability subscore and by the impact subscore of the CVSS. And then if you put this all together, and this is what we have shown in our paper here, then you can actually see that using the game theory, you can improve the software vulnerability patching approach based on a combination of the CVSS score and the Nash equilibrium, which is a very interesting outcome. So I would like to conclude this lecture now by summarizing what we have done. We have outlined two recent game theoretical applications to our two case studies, and one of them was using massive security games for the YouTube channel attack situation, where the main point was a large number of targets and a more sophisticated and more efficient data structure to store the game, hence making it possible to solve it. And then we have looked at a strategic game, a small game with simply two strategies for both players for the analysis of the vulnerability patching game. And here the interesting aspect was that we were able to use the common vulnerability scoring system, which is an open standard and well known to the practitioners. And we have used some of the information in the subscores as in order to inform the game. And then when we solve it, it turns out that there's a mixed Nash equilibrium, which can basically give more information than if we didn't have that theory available. Let me remind you that game theory is only useful if it's accepted by the different participants. Otherwise, it would be pointless. And that's where the game theory still has to work in order to convince more and more people and gain a larger audience. And then in terms of the future, what could the future bring for the game theory? I mean, in my opinion, these models will become more mainstream. They will be more accepted. And really what we would want to do is to build standards. And obviously computer security is mainly driven by creating standards for communication, for assessing the security of an organization. So if we were able to, let's say, inform the risk assessment approach, such as in one of the standards, this ISO 27000, if that did have some game theoretical components in it, then the game theory would have found a real appreciation and usefulness amongst practitioners. I would like to thank the Cyber 2020 Conference Organizing Committee for inviting me for this keynote. I would like to thank the audience for attending the lecture, and I hope to meet you one day in person. Thank you very much again.